Ja, välkomna allihopa till det här seminariet i vår serie om elektromobilitet. Riktigt kul att så många har anmält sig. Vi är väl runt 100 som har anmält sig, så vi ser hur många som droppar in. Jag heter Kristoffer. Jag kommer vara moderator idag och leda frågor och hålla ordning på saker och ting. Tillsammans har jag Martin med mig här som är tekniker. Vi arbetar på MITC, så det är vi som håller i det här. Och idag ska vi prata om bränsleceller. Och det blir mycket spännande. Och med oss har vi Valentina och Johan som kommer guida oss igenom det här. Innan vi drar igång så vill jag puffa lite för några saker som händer framöver. Den 25 april så har vi en hel dag inom projektet Transmission som handlar just om omställning i fordonsindustrin. Vi kommer bland annat prata mer om vätgas. Vi kommer prata om framtidens hållbara gruva. Vi kommer få höra från olika underleverantörer hur man hanterar omställningen. Vi kommer få med oss Polestar som pratar om cirkularitet i fordonsindustrin. Massa spännande saker på det schemat. Så var med och anmäl dig där när den inbjudan kommer upp inom kort. Jag vill också puffa för nästa event som vi spikat redan den 20 april. Då kommer vi prata om Second Life för fordonsbatterier. Så det blir riktigt intressant också. Temat cirkularitet, affärsmodeller och design guidelines för att kunna hantera det här. Man förutspår att det kommer vara ungefär 250 000 ton pensionerade batterier inom kort. Så att någonting behöver vi göra med de här då. Så det kommer vi prata om då. Men nu ska vi prata om bränsleceller. Det förväntas bli mer än 45 000 bränslecellselektriska fordon i Europa runt 2030. Det kommer byggas vätgaskorridorer med massor med tankstationer. Men det är fortfarande öppet vilka applikationer för bränsleceller som kommer vara mest kostnadseffektiva. Så det kommer vi prata om idag. I'm going to switch to English now because the presentation is going to be in English. So I'm going to welcome Valentina Zakaria. Did I pronounce that correct? Zakaria?
Yes, thank you.
Thank
Zakaria,
you.
yes.
And Joanna. So welcome both of you and thank you very much for joining us here. It's going to be super interesting to see what you have to present and the discussion. So take it away. Thank you very much.
Thank you very much. It's really great to see how many people are here. As Christoph said, we are going to talk about fuel cells and hydrogen today. And in case you have you participated to the previous webinar of this series, that was focusing more, it was covering aspect of hydrogen production and distribution. But today we're gonna look at the end side of it. So how we can then use hydrogen to convert it into electricity to drive electrical motors for cars, trucks, and so on. So in the first part of the seminar, I will cover some fundamentals of fuel cells. So covering the working principle of this conversion between hydrogen and electricity. And introduce what are the other components and the other elements that we need in the system for fuel cell propulsion. And give some also consideration about the lifetime. And put it in the hydrogen into context of this electromobility. Then we're going to have a first little break for questions about my part, and then Johan will come and talk more about really practical aspects of how the machines are going to change if we are using fuel cell to drive the electrical motor. So what are all the practical issues that we have to consider in the powertrain and so on. So let me start with actually giving a bit of context and putting hydrogen into the context of electromobility. I mean, when we talk about the goal of electromobility is to really decarbonize the transport sector, which is right now one of the most challenging sector to be fossil free. And of course, in this view, we see that the most of the work will be done by battery-driven vehicles. But there are some niches in the transport sector where we can see that actually hydrogen can have much more promising application than battery. And that's mainly due to the limitations of batteries. So we know that it comes down to the question of how is the energy stored. Actually, batteries and fuel cells, they use essentially the same principle for working. We want to transform chemical energy into electrical energy. So we have a cell that has a positive side and negative side. We have reaction inside and electrons that are transferred through an external circuit, and that can give us electricity that we can use to drive a motor or other equipment. So this is essentially the same, whether we have the chemical compound that we're using is lithium carbonate or is hydrogen. But the big difference is where the energy is stored. In the batteries, the chemical compounds that give us the energy is stored inside the cell itself. So this, of course, leads to some limitations in the power density and the weight or the size of the battery. Like in very simple words, if I want to have a more powerful battery, I need a bigger battery. So this, of course, can lead to some limitations. The difference when we have a fuel cell is that we can store energy outside the cell. We store energy in the form of hydrogen. Therefore, the volume of the fuel cell is not directly related to the power that a fuel cell can deliver. We can have very compact and light cells and still have a high power density. So this is the main advantage. So in all those applications where high power density, long driving range or long autonomy, or really short charging time are of utmost importance, we see that hydrogen can bring a clear advantage over batteries. So this is to put a bit into the context. Now let's look a bit closer to a fuel cell, how a fuel cell works. As I said, it's not very different from a battery, so the same concept applies here. If we really zoom in and look at the fuel cell very close, we see that essentially as a battery, it has a positive side and a negative side, where this chemical reaction occurs. There are current collectors on both sides to collect the electrical current, and there is a membrane in between the two electrodes. That in the type of fuel cells that are mostly used for mobility, this is a polymeric material that constitutes the membrane. So this type of fuel cell are called PEM, or polymer exchange membrane. Of course, because of the material that constitutes the membrane. And this type of fuel cell operate usually between 40 and 80 degrees Celsius, and a low pressure, atmospheric pressure up to 3-4 bar, and the most common applications. The way the fuel cell works is that on the negative side, we have usually hydrogen, in this case, flowing through. And that's the element, the chemical element that is oxidized. And on the positive electrode, we use the oxygen from air. So we can simply use air to flow through the fuel cell, and the oxygen is used in the reaction. So because only hydrogen and oxygen react, the only product is water. So it's a very clean technology. It doesn't produce any CO2 or anything else. So of course, we can consider it completely fossil-free if the hydrogen is also produced in a fossil-free way. So green hydrogen from electrolysis, for example. One single cell it's really small, and it actually produces generates less than 1 watt in power. But we can stack thousands of cells together, either in series or in parallel, depending on the amount of power that we want to reach. And the important characteristic here is that the performance is not so dependent on the size of the overall stack, because the performance of one cell, it's very modular. So if we have one cell, we can stack together a lot of cells. So the performance doesn't really change if we have one cell or a million cells. As I mentioned, we can consider it as zero emissions technology, and not only when it comes to CO2, but of course also NOx or other emissions. If we compare to traditional internal combustion engines, we have no combustion inside a fuel cell. So there is no emissions that are connected to the combustion. If we only have hydrogen and oxygen, the only product will be water and water vapor. Also, there are no moving parts. So this is an advantage it can ensure that we have a longer lifetime of some of the components, less need for maintenance, although I will talk a bit more about the lifetime consideration for the fuel cell, which is different. And it's when it comes to polymer exchange membrane, these are very compact and lightweight, as I said, which is very advantageous for electromobility applications. Now, I want to explain a bit more in detail how the fuel cell works and what is the performance that we can expect. So we have an ideal voltage in between the two electrodes that is simply given by the ideal amount of energy that we can release from the reaction between hydrogen and oxygen. So this is the ideal voltage in standard condition in terms of temperature and pressure. This is, of course, not the real voltage that we can expect to have between the two electrodes. First of all, because we have an effect due to the temperature and the pressure, which lowered the voltage from the ideal case. So we refer to it as a nurse potential or nurse voltage. But the open circuit voltage is even lower, and that's because there is energy that is spent just to activate the reaction of hydrogen and oxygen. And then from the open circuit voltage, what you see here on the screen is the characteristic curve of all type of fuel cells, of the voltage versus the current. So as we increase the current that we draw from the electrodes, we see a decrease in voltage with this particular shape. The difference from the open circuit voltage and the actual voltage can be related to different type of losses. Some that are related to the reactions itself, so kinetic losses. We have ohmic losses because of the electrical charges that have to go through the membrane, and mass transfer losses. And if you look at this shape, we can see that for really low current, the kinetic losses are the dominant one, and they follow kind of a logarithmic trend. Then there is usually a very large range in which the voltage decreases linearly with the current, because the losses are mainly driven by ohmic losses. And then a region with very high current, where the mass transfer losses are dominant, and we have a really steep, almost exponential drop in voltage. So it is clear how it is usually appropriate to work in this linear part of the curve, where we have mostly the effect of ohmic losses, and it's very easy to relate from current and voltage. Now, because the power is the product of current and voltage, we can see that the power has a trend like this, where it increases with increasing current up to a certain maximum point, and then for even higher current, the power will drop because the voltage now is dropping too low. And so there is always a certain point where we have the maximum power from the fuel cell, which is at quite high current. But the maximum efficiency, it's at low current, where we have higher voltage. So this is a bit particular of fuel cells. Most of the other systems that we use to convert energy, they usually operate in a way that the maximum power is also the maximum efficiency point. In a fuel cell, we have a bit of a trade-off in this sense. So if we work at maximum power, we usually operate at much lower efficiency. So that means that the operating point could be somewhere maybe in the middle, where we can have a trade-off between high power and high efficiency. But this also makes it interesting because unlike most of the other systems and engines, when we decrease the power, we usually have higher efficiency, which it doesn't happen in traditional engines, for example. But then let's look at the fuel cell in the context of propulsion. What are the other elements that are needed around the stack? So we know now that how the fuel cell works. We feed hydrogen, we draw some current, and then now we have electricity to drive the motor. But what are the other components that are needed around it to make it work? First, very important components that I'm going to mention is fuel and air conditioning systems, and in particular, the need for humidification. That's because the in PEM fuel cells, as I mentioned, the membrane is a polymeric material. The most common use is Nafion. That's the commercial name of the material. So one important requirement for it is that it should always be humidified with a certain range of humidity. So we always need water in the liquid form with a certain thickness that surrounds the whole membrane. Otherwise, the membrane just doesn't work properly. The conduction property of the membrane drops, and so we cannot. The membrane cannot really transfer electrical charges from one side to the other of the cell. And it happens in both extremes, both if the membrane is too dry or if there is too much water, and then we have flooding in the fuel cell. So this requires a really an appropriate water management system and to control the amount of water that is flowing through the fuel cell, because if you remember, water is a product anyway of the reactions that happen in the fuel cell. So water is produced inside, so it needs to be removed at a certain rate in order to keep always this humidification constant. So humidification of hydrogen and air needs to be controlled, and also the rate at which the water is removed from the fuel cell. So this is the first really important part that needs to be there. And then we have, of course, a cooling circuit. Johan later on will probably give you a bit more details about that. But as I mentioned, the fuel cell operates a temperature between 40 and 80 degrees, with higher temperature leading to higher efficiency. So if we want better performance, it would be most probably closer to 80 degrees. But because of this requirement for the membrane to be always humidified with water in liquid form, it's important that the temperature doesn't exceed 80 or 90 degrees, and otherwise we would start to have water evaporation, and that would lead to membrane degradation. So the temperature also needs to be controlled quite tightly. So we need a circuit, a cooling circuit to cool down the stack. Water is commonly used as a cooling medium. And then there needs to be, of course, some sort of heat exchanger radiator to reject the heat. Another set of components are all the power electronics needed and a battery system that is very, let's say, desired in the fuel cell propulsion configuration because of two reasons, actually. One is because we can take advantage, actually, of the battery to get maybe to use regenerative braking to store some energy when the vehicle brakes, and then boost up the power when we need to accelerate. So it can be advantageous to include a battery to take advantage of this type of energy storage. But another element is very important to mention is actually how we can extend the lifetime of the fuel cell, because although PEM fuel cells are quite good to handle transients, so acceleration, deceleration, and that's why this type of fuel cell is good for transportation. There is still a limit. So very fast acceleration, very fast deceleration can shorten the lifetime of the fuel cell, can just degrade the materials of the fuel cell faster. So it is actually very beneficial to have a battery to support the fuel cell during these fast transients. And therefore, we need then a good energy management system that controls when and how the power is split between fuel cell and batteries in different conditions. So then we have all these power electronics and control systems, and then finally we can have an electrical motor to move the vehicle. I was about to forget, of course, hydrogen tank as well. It's a fundamental element here. And for land-based transportation, we are usually talking about compressed hydrogen, 350 bar or 700 bars, depending on the size of the vehicles and the applications. Of course, when we then talk about aerospace application, we are looking into liquid hydrogen. And for maritime application also, I want to mention just one other option for hydrogen storage, which is being right now tested on some ships. That is metal hydride. Metal hydride in metal hydride, essentially the hydrogen is absorbed into the structure of a metal. And the advantage of this system is that it is less energy consumed, like it consumes less energy to store the hydrogen, which is one of the big disadvantages of, in general, storing hydrogen. Either we have to compress or cool it down to liquefied. That's a lot of energy that is needed. So the cost then become quite high. So the solution of metal hydride can be a bit cheaper. Of course, the weight is quite considerable, because we are talking about 100 kilo of metal hydride to store 1.4 kilo of hydrogen. But then the characteristic of the metal hydride is that it needs some heat to release the hydrogen. And the heat that is needed is around 40 to 65 degrees, which is actually the operating temperature of the fuel cell. So then we have a perfect coupling here, because the cooling circuit of the fuel cell can be also used to provide heat to the hydrogen storage to release the hydrogen. And of course, when we need more hydrogen, it's because the fuel cell is operating higher power, so it's producing more heat. So this is a perfect coupling. And then we have this heat exchanger in between. So I just thought to mention this, not very relevant for land transportation, but it is looking at more in detail for maritime naval transportations. So just to summarize then what I showed before, what is needed to make a fuel cell work to use hydrogen in a car or a truck. We need the conditioning system for the air and the fuel, hydrogen storage tank, thermal management system, water management, really important, power electronics, batteries with some also control of how much power is split in between the two. So just to give a bit of consideration of the lifetime of the fuel cell, as I promised, here you can see what are the targets right now that we have in front of us, of 25,000 hours operating hours for light duty vehicle and heavy duty trucks, and 40,000 hours for railway applications. And I know now the most the question that would come is, are we close to these targets? Are we meeting these targets? What is that? And the answer that I have is actually that we don't know. We still don't know so well, because I mean, for batteries we have done. There has been extensive research and work, but fuel cells are still maybe a less mature technology, especially when it comes to commercial applications. So there is a bit less thorough test on like real road conditions of different vehicles. Mostly there have been accelerated tests in the lab. So we know that we expect that we can meet these targets, but there is still, I guess, not enough data out there and results out there to have a really complete picture. When it comes to reasons why the fuel cell lifetime can be limited, I want to cite here just two main reasons. And one is what I already mentioned, is the need for the membrane to always be humidified with a perfect amount of water. So if that doesn't happen, we can go on both extremes. We can have membrane flooding when there is too much water, or membrane drying. And both conditions cause, of course, the membrane to stop working properly. So the performance of the fuel cell is way below what we expect. So to avoid or prevent this problem, as I mentioned, it's very important to have a really good conditioning system and good water management. But then there is another aspect that is quite inevitable, unfortunately, that is the aging of the catalyst. So PEM fuel cell use usually platinum as a catalyst, and over time it can react with other materials, or different things happen so that we lose part of the catalyst and the fuel cell doesn't work properly. So this is, of course, on one side a matter of having better materials, so more material science study to improve the fuel cell materials. But what we can do in operation is to have a good energy management system, because as I mentioned, we can really extend the lifetime if we can avoid very sharp acceleration and deceleration. So if we have battery system and a good control system to use the battery when it's needed and in aid of the fuel cell, then we can really extend the lifetime. So to conclude my part, I want to just circle back and go back to what I was saying at the beginning, the context of hydrogen in electromobility. You all know that hydrogen is a very promising energy carrier. It can be produced from many sources, so green hydrogen could be the answers to a lot of problems. It's very flexible. We can, you know, when it comes also to energy storage for long term and transportation, it can be more flexible than to transport electricity. And the only product, if both of combustion, if we have combustion of hydrogen, but even more if we have electrochemical reaction in the fuel cell, the only product is water. So it can really be the answer for zero emission transportation. When it comes to the use of hydrogen in PEM fuel cells, I have to mention this, that the PEM require really pure hydrogen because they're definitely not tolerant to any small impurity. So this could add cost for the hydrogen treatment before it can be use to fuel up the car, because the requirements for purity are really, really stringent. There are other fuel cells that operate at much higher temperature, and they are tolerant of impurities, or they can even work with other fuels. And I think this is quite important to mention, because a lot of time when we talk about hydrogen, then we consider that maybe we should use other energy carriers that can carry hydrogen, like methane or methanol or ammonia. Then there are high temperature fuel cells that can operate directly with this type of fuels. So then we don't have to go back to hydrogen. But these are, first of all, a bit less mature technology than PEM, because they operate at higher temperature. Then the transients, the way they handle transient, and also the amount of time needed to start up is different, it's much longer. So they are not necessarily the perfect answer for transportation, at least in some sectors, but they could be a promising solution for some other specific sector. I'm thinking especially maybe for ships. So this is my part. I think we have a couple of minutes for questions. And of course, if there are additional questions, you can also feel free to email me. But then otherwise, you can also take that at the end after Johan's presentation.
So we have a question here from the chat. It's Tor. He's asking, what is the typical level of water humidity in the fuel cell?
I don't have a number in my head, because I think it depends on the operating condition and the fuel cell types. Like it depends on some factors. So actually, maybe let me look at some more precise number, and I can get back to that at the end of Johan's presentation.
Can I add a question? Can I add a question to that? Because I was actually, this is Tor speaking. Thank you, Valentina. What is the consequence if the cell goes dry or too wet? Is there an irreversible, let's say, deterioration, or what happens?
Yes, so in most cases it's reversible. So yeah, thank you for asking that. Because of course, if it hasn't been operating for too long in like too dry condition or too wet condition, so the performance can be completely brought back. But of course, yeah, I guess it depends if it operated for extended amount of time in a condition that is not ideal. That could lead to also irreversible consequences.
Thank you. I hope you get your answer there, Tor. We also have Jacob. What happened? The question is, what happens if the stack freezes? And what is the normal way of handling low temperatures?
That is a very good question.
Do you want me to fill in there, Valentina?
Yes, maybe you have a...
Yeah, since that's a topic we have been working quite extensively on. The first and the easy question is that you don't allow it to freeze, because after you have shut it down, you try to dry it up as much as possible. And then if something would happen that makes you have water left in the cell when it shuts down due to a malfunction or something, then you basically get a little area if the cell is this big, you have a little area that is not freezed that will start to warm up and then heat over the cell. That's a very ineffective way of starting it, but that is what would happen. But the basic question is that when it's below some degrees, you try to dry the cell as much as possible to avoid the water.
Yes, a follow-up question from myself here. Is there a risk of deformation since the water expands when it freezes? Is that, or do you need to take that into consideration when designing to be able to handle those forces? Even though I mean, if one part is still unfrozen but the rest is frozen, would that kind of deform stuff physically?
That is nothing that I have ever experienced when we have frozen stacks.
Yeah, I mean, the materials are quite sensitive, but I guess, I mean, they are designed also to work under pressure. So I think if the amount of ice anyway, it's very limited because we are trying to be very limited. So it shouldn't be a major problem, but it all depends how much water is left there that freezes.
We also have a question here from Kurt. Is there any research on ammonia fuel cells in Sweden? You know,
I don't
Valentina?
think in Sweden, not that I know of, at least maybe, but that's could be just my ignorance. There is a lot of research ammonia fuel cells in different parts of the world. Japan is one of the leader in this research, but that I know of, I don't know if anyone in Sweden is looking at that.
Okay, thank you. Now we also have a raised hand from Wilhelm. You have a question?
Thank you. Thank you, Valentina, for a very nice presentation. I have a question regarding your sum up slide. If you can move back, please. Maybe I misunderstood one part there. It's not regarding the fuel cells, it's more like regarding the hydrogen. You're stating that the product of combustion is water. Is that entirely correct? Don't you get other products as well, for example, NOx?
Yes, so yeah, maybe I didn't say this correctly. So of course, if we have only hydrogen used in a fuel cell, in that case, the only product is water because there is no combustion. Yes. If there is combustion, yes, there is of course a problem or with handling NOx because the combustion happens at really high temperature. So then, yeah, there are ways to avoid or reduce NOx, but then it's a matter of combustor design and a lot more details there. But you're right. Yes.
Okay. Okay, that was my question. Thank you very much.
Yeah.
I have one. Unless there are any, I don't think we have any more raised hands. I have one last question here. Where you talked about the battery. If we look at the battery size in a fuel cell application compared to a pure electric battery electric application, what would you say the size would be needed? Is it like 1/10 or one? I mean, could you say give a ratio or some?
Yeah. So to have a good answer here, I think we need to talk a lot. So I will try to give a short answer because, and maybe actually Johan will also touch upon that in his part. But of course, we need a much smaller battery because we don't need the whole power to drive the whole vehicle, for example. We need a battery just big enough to support during acceleration. So, but the optimal size, I think it depends also really on how much maybe we want to handle this power split consideration about the lifetime of the fuel cell. So I think there is not really an easy answer to say it's great to have a battery that is a 10th of the size of the fuel cell, for example, because just because the studies around this and how we can handle the lifetime extension are not so many, are not still so conclusive. So I can give some like ballpark number, but it's really I don't know what the optimum size should be because it's still not known.
Good. Should we hand over to Johan here?
So I will start off with sharing our little perspective of hydrogen, and then I will start by speaking of this machine that have been shown, called Elkalle or Electric Charlie. That is a joint research project between a couple of Swedish partners, with the aim of building a technology demonstrator. This is not a machine that we aim to sell at this stage. It's just to show that the technology for doing this exists, and we will continue to test it and so forth. So we are going from a laboratory research to actually doing real machines and vehicles. We have also released a truck that is officially known, so we are testing that as well. Just to summarize a little, the theory Valentina explained to actually the real machine is that this machine ended up being far lighter than we expected, due to that the weight of the fuel cell is so much less than a battery or even a combustion engine. And for this kind of machines, the weight is, the lighter the vehicle is, the more you can carry. So you earn more money in the end, instead of just hauling around batteries. That is the risk. So that machine is in US right now and will be showed off at a very big expo called ConExpo in Las Vegas. I believe it's next week. And then we will take it home and continue test it, but so far it have been really promising. And then why should we go to hydrogen? I mean, what is the driver besides that it's there and you can do it? So basically, if you have green hydrogen, it's electricity in a bottle. I like to say. And building more and more renewable energy sources, wind and solar and water, and so you have even bigger losses. Today it's between 30 and 35% of all the green energy that we cannot harvest because there is no load to handle it. So already there is a great potential of setting up electrolyzers and cracking water to green hydrogen. So this gives us that we have a potential production cost of 1 to 3 euros in the future, not today. This is ambitions to the later part of this decade. And then you should remember that hydrogen have 33 kilowatt hours per kilogram, meaning that it's 3 times more energy dense than diesel or gasoline. So then you have electricity that you can store and transport. You can either store it long time in salt caves, over years even, or you can transport it either by truck, by ship, or by pipeline. And that can be done through the globe. There is initiatives in both Africa and Middle East where they will transport solar energy from those areas through hydrogen, starting from 2024, I believe, in Namibia. And in Europe, we have something called hydrogen backbone that is shown on this map, which is basically the hydrogen gas infrastructure that is being updated and built as we speak. So you're able to transport hydrogen through pipeline between the southern part of Spain all the way up to Luleå and Kiruna in north of Sweden. And for us, as a vehicle manufacturer, the big driver is that we need to have solutions for high energy consumption vehicles, meaning that long haul trucks need to reach 1,000 kilometers in 1 day, more or less, meaning on one charge or one fueling. And our yellow machines need to operate an 8-hour shift. And that is, for some applications, very hard to reach today with batteries. So there we see this as the solution, or one solution. There will be several solutions. So what is the benefit of doing this? Yeah, well, basically you end up with an electric machine that we need to have regardless of if it's a fuel cell or if it's a battery. We need to have the same powertrain behind it. So I'm not comparing here the possibility to recoupling brake energy for the energy reduction and so on. I'm just comparing apple to apple here. So we have the possibility to then have a range of 8 to 10 hours of machine usage, or 1,000 kilometers on trucks. We can have continuous high energy output, meaning that, as Valentina said, there is a split between energy and power. And that you don't have in a battery, because if you have this amount of energy, you get this amount of power. But here you have the size of the fuel cell, say how much power you can get, and the size of the tank, say how much energy you can harvest of it. And we will end up with a refueling time of approximately 10 minutes in compressed gas. I should just clarify that is not today, because ISO is working on a standard refueling protocol that have not existed before, so it been best engineering practice, and then there have been some challenges there. But we will end up with 10 minutes here in a few years. So that is on what's upcoming on the machine level. Then if we deep dive a little into maybe the most important technologies or technical areas, maybe I should say. Cooling, as Valentina said, due to the electrochemical reaction, basically almost 50% of the losses or the total energy consumption is in heat, because we don't have any exhaust mass flow as an engine do. So we have more energy to the cooling system, and we need to cool it at a lower temperature. A PEM like to work in around 80 degrees compared to an engine that is closer to 100 degrees. And that means that higher heat reaction gives a bigger cooling package, and lower coolant temp gives a higher heat reaction. So we get an even bigger cooling system, meaning that we will have a huge cooling system and very big cooling capacities. But if we do this in a smart way, with some sort of look ahead or road ahead or whatever it's called these days, to see what are the loads that comes in front of us, so we can start to charge up the battery a little, or we can cool down the fuel cell a little to have it the possibility that when you go uphill you can let it warm up, because you know that there will be a downhill where you can cool it off and stuff like that. And as the fuel cell behaves, you get an even higher loss at the higher load. The efficiency decreases, so you have even more, since you're injecting the same amount of hydrogen, but at a lower efficiency, you create even more heat at the peak load than compared to the best points. And then not only the hydrogen needs to be very clean, the air needs to be very clean in the system as well. Since the fuel cell is sensitive to gases, that causes most in most cases corrosion on the catalyst. This is today solved by using active carbon filters. But the problem with the carbon filter is you can never detect without having a laboratory when the filter is saturated with gases. So it's not like a conventional particle filter that you have today, that you can see that it's kind of filled with debris. So here I believe that the suppliers have a huge potential in creating state-of-the-art solutions for determining when gas saturation occurs in the filter, and also come up with the optimum coal doping setup, meaning that you can do active carbon in different layers with different characteristics to absorb different kind of gases, depending on if you're in a mine or on a road or in a quarry or whatever. And that I don't think will be led by the vehicle manufacturers. Then storage system. Today state of the art is 700 bar compressed gas. That is what is used on the existing vehicles on the road, with the exception of some buses that are 350, but it's the same kind of technology. The technology is there. You can go and kind of buy it off the shelf at suppliers. But the challenge here is that it's produced from carbon and epoxy, which is not recyclable for this time being, meaning that they need to be scrapped and thrown away, more or less. So for this to get big scale, I think you need to think about how can you recycle it in an environmental friendly way, and how can you manufacture the tanks with a good cost. Because right now you need to spin a lot of carbon fibers around a cylinder. That's very labor intense. Even though it's done by robots, it's still very, very time consuming, which drives the costs even more. And hydrogen does not exist only in gaseous form. You can cool it down and then you get it into a liquid form with a higher energy density. But on the other hand, it's very, very, very cold. You need to go down to 20 Kelvin, which is minus 253 degrees. But then you almost have doubled the amount of hydrogen you can carry with you, since you get up to 71 kilos per cubic meter compared to 42. I don't think I have stated this here. But compressed in 700 bar, it's like 42 kilos per cubic meter. And you only have, even though it sounds very extreme to have a liquid that cold, the tank you have is a stainless steel thermos, more or less, very similar to what is used in natural gas tanks today. And those are commercially available at vehicle levels and ships and so forth. And a lot of hydrogen today is already liquefied, but not used in vehicle industry, rather than in chemistry industry and the medical industry. And for our situation, where our machines don't get to the fuel station, rather the fuel station gets to the machine, if you have an excavator or a wheel loader or something like that, then it's a really challenge to bring the hydrogen to the user, both to the site and then to the machine. And then it's even easier if you have it in liquid form to have it compared to have it in gaseous form. And then there also exists something called cryocompressed hydrogen. That is when hydrogen gets a supercritical form. So it's cold and it's compressed, as shown in this picture. And then you can get up to 80 kilos per cubic meter. But this does not exist commercially today. That is extensive research ongoing in the area, but it doesn't exist yet. And then on top of that, we are doing things with ammonia and different kind of carriers as well, as Valentina briefly mentioned. And refueling in gaseous form. As I said, there is a high-speed refueling protocol being developed. These kind of commercial refueling stations exist all around the globe, even though they are not too many of them, as it is with conventional fuels. But we have 5 or 6 in Sweden at the moment, I believe, and there is at least 100 of them in Germany. And connected to these hydrogen corridors, it's stated that within the European Union, it should be 1 in every 100 kilometers on the big roads throughout Europe. And the standard dispenser is designed and is the one to use, so to say. So there is no question about that. It's really just go ahead, more or less. And then my last slide and my conclusions. As we said, the power split between fuel cell and batteries is very, very complex. And for the time being, the right solution can only be determined at vehicle level. You need to know what kind of vehicle will you build and how will it be used. So you really need to... oh, shit. Sorry, everyone. My vacuum cleaner just decided to turn on. So you need to know your customer and the work really, really good to be able to do the perfect powertrain split. And then you also need to consider, what do you want to sacrifice? Do you want to sacrifice cost, performance, or lifetime? And what component do you want to sacrifice first? The battery, the fuel cell stack, or any other component? You need to determine the weakest point in the chain. It is not possible to have a perfect chain, because then you will end up with having too high cost, and then it's not the perfect chain anymore. So that is something that we can discuss for hours and hours, and I said you can do a PhD on that if you want. But it's a big challenge for sure. And that was my last slide, and I'm still 1 minute over time. So yeah, thank you for your attention. And do we have any questions?
Thank you, guys. And first, we have some questions. Thank you, everybody that was viewing in or joining. And if you need to leave, so that's all fine. But let's take the questions here. If you have the time to stay, so please stay. We have a question from Joachim. What about leakage of hydrogen in these high pressures, 700 bars?
Yeah, you only have 700 bar in the tank itself. Then directly after the tank, you have a pressure reducer. So it's only in the tank that it's this high pressure, and then the tank is more or less indestructible. So you can't have a 700 bar leakage, more or less.
Thank you. I hope you got your answer there, Joachim. I think that's it. We have a raised hand. Perhaps it was from earlier. Let's see. It's Tor.
No. Yes. Can I just ask you one very impressive project there with the excavator or the dumper? Can you just give us a hint on what the total weight? I mean, comparing the weight of hydrogen compared to batteries is not really correct, right? So it's storage and it's safety measures and everything. Can you give us an idea the comparative weight on a battery, on what the installation of the hydrogen tanks and safety measures were in total, or did you ever do that calculation?
Not apples to apples, but kind of close, just a rough figure, 2 tons.
Okay, and what Would that amount of energy required generated? How much tons of batteries would that have been?
Yeah, I can't say that this weight this much and this weight this much, but I know that the delta was roughly 2 tons. If you should have the same,
the delta was okay.
Yeah, if you should carry the same amount of energy with you.
Fantastic! Thanks, John. Perfect.
I think there's let's see, any more questions? I have a question, more of a thought perhaps. Is there any research ongoing, because there was a lot of residual heat to take care of? I guess there would be a lot of research looking in what to do with this heat, because it's energy, or low grade energy, but still energy in some ways. So so is there any future in this application area, or is that kind of not considered right now?
No, it's huge amounts of kilowatt hours we are throwing out through the chimney, more or less. The challenge there is that the temperature is low, so it's hard to harvest that energy. But for sure, I know both in the academia, in the industry, research is ongoing.
Cool. So we have Pontus raised the hand here.
Yeah, I have a question. I mean, you are from VC and so am I. And what is the biggest challenge when it comes to construction machines? We know that both loaders especially and also excavators have a very cyclical load in the work cycles.
You mean in terms of performance and behavior, or?
Yeah, performance and behavior,
Yeah, then you go back to what I said about the power split. You really need to know what the machine will do in order to do the proper dimensioning between energy provider and power provider.
Yeah, because I mean that it is a big challenge already today with the combustion engine and so on. So it's I guess it will not be easier with the fuel cells and so on.
No, but it's the same with the batteries. It's not like there exists one battery cell, and that is the one that people are using. You have a vast variety of different containments and different characteristics. So it's the same here. You need to know your thing.
Thanks.
So we have a question from Kurt, or a statement and a question. We have the infrastructure of ammonia already. Why not use it and complete with pipelines?
Yeah, I think the biggest reason there is that ammonia is very, very poisonous. But ammonia for sure is ongoing. They are transporting big amounts of green ammonia. So you can do electricity, produce hydrogen, add up with nitrogen to create ammonia, transport that to, let's say, Europe, for instance. I know that Rotterdam are taking a lot of big amounts. Then you do green fertilizer of some chunk of it, and then you distribute the rest of the ammonia as energy. Then the question gets to, do you want to reform the ammonia to hydrogen at the machine, or at the site, or in the city, or in the state, or? Yeah. I totally agree. So I mean, for sure, we want to use it, and everyone in the industry wants to use it, but where does it fit? That I think is the biggest answer that we are trying to work on, and you will have a total energy landscape that in the end will get to electricity in one way or another, but how that looks depends on where you are in Europe or in the world, if you have pipelines, and if you're have a strong grid, or if you have a weak grid, and yeah, it's a complex one.
Yeah, good. Thank you, guys. Super interesting. Thank you, Johan, and thank you, Valentin. Really, really good presentations, and really interesting to see the basic technology stuff and also the challenges. There's a lot of things here for potential sub-suppliers and other actors to bite into to help drive this development forward for sure. So good. I think if there's no more questions, I cannot see anywhere anymore in the chat, and there is now we got one here. I imagine that all the tests carried out have been at sea level. My question is if they have considered work at height above 3,000 meters of altitude.
Yes. We have tested that, and we have ambitions for that as well. So yes, it's considered.
It's considered. Okay, thank you. Any more questions? Feel free to raise the hand, write in the chat, or just shout it out. And that's it. So thank you very much. Thank you, Johan and Valentina again. Thank you all for participating. It's really fun to have all you joining in. We have about 100 people every time we do this, so it's really appreciated. And remember, the recording will be put up on our webpage very soon. And also, I want to puff again for the next seminar on the 20th of April, vehicle battery second life. It's going to be super interesting to see how can we make up business models and what's needed to use the batteries that are still valuable but not suited for life in a vehicle. So that's going to be discussed at that point. So thank you very much and have a good day.
Thank you.
Thank you.
Bye.